The subject of this lecture is difficult. It is not difficult because it involves difficult equations. In fact, you'll find that most of the equations that I describe here are simple. The subject is difficult because it involves what is perhaps the most difficult problem that humanity has to solve, either from a heat transfer perspective or from a purely societal perspective this century. And the weight of the responsibility of trying to solve that problem carries with it a large emotional burden, a burden that we nevertheless have to carry. The subject of this lecture is thermoregulation, the process via which the human body attempts to maintain ideal thermal conditions, and what happens to that thermoregulation process whenever the body is exposed to extreme heat events. So just as a reminder, the human body is both an engine and a thermostat. It converts chemical energy in the form of food into both thermal and mechanical energy that we use to do the things that we humans do. And that thermal energy isn't just a byproduct of that process via which we convert chemical energy into mechanical energy. It's also a fundamental part of the way that the human body attempts to maintain itself at ideal thermal conditions. As you may remember from way back near the beginning of these lectures, the human body really likes to stay near 37 degrees Celsius or 98.6 degrees Fahrenheit, give or take a couple of degrees depending on the body. But the point is that the human body isn't just an engine, it's a thermostat. It maintains itself through a control system as close as it can get to 37 degrees Celsius. And the fact that the human body is constantly generating heat and the fact that the human body wants to stay at roughly this temperature means that we have to be exposed to lower ambient temperatures than the temperature of our body, right? Because that thermal energy that we're generating needs to flow out into the environment in order for us to stay at a constant temperature. Now, of course, that ideal ambient temperature will depend on the characteristics of the body that we're trying to describe, but usually, optimally, people like to prefer to be around somewhere between 20 and 25 degrees Celsius. And the way that we can model the heat transfer that's occurring in those ideal conditions is simply by using the equation that models heat transfer between two different objects. We can describe the heat transfer rate Q out of the human body as being equal to the difference in temperatures between the human body and the environment, delta T, times the surface area of the human body, AS, times the heat transfer coefficient, where all of the mysterious physics of heat transfer get dumped into, some mysterious heat transfer coefficient H. And so we can use this simple equation to try to understand what happens whenever we perturb, some of the values associated with ideal thermal conditions in the body. And one thing that we should take a look at is the fact that even though we like to live, even though our bodies prefer to exist in ambient temperatures that are between 20 and 25 degrees Celsius, humans have lived and thrived in environments that are much colder or much warmer than that. And the mechanism via which they are able to do so, where the human body is able to exist at temperatures that are not the ideal temperature, so to speak, the process that allows this to occur is called thermoregulation. So like I mentioned before, thermoregulation is just the body's way of trying to maintain that ideal operating temperature of 37 degrees Celsius amidst varying ambient temperatures. And so you can think of it almost like a control system where we try to fix as much as we can the body's temperature. We observe changes in the ambient temperature, causing fluctuations in the delta T. And so the human body attempts to alter the other variables that it can in the equation Q equal to HAS delta T in order to maintain as much as it can that body temperature of 37 degrees Celsius. Now, for now at least, the human body does not know a way to increase or decrease its surface area. And so really most of the efforts of thermoregulation go into altering Q or H, to altering how much heat the body is releasing, which is very rare. There is one mechanism that does it, but it's quite difficult, right? It only happens under specific conditions. And by altering the heat transfer coefficient that governs the heat transfer between the human body and the environment. So what are some examples of these processes? So, well, when the ambient temperature is too low, we call those hypothermic conditions, the difference in temperatures, that delta T, is too large. And in order to compensate, what the body does is it tries to shiver. That shivering is a process via which the mechanical energy going into the shivering, going into the actuation of your muscles, that mechanical energy is turned into thermal energy, so creating another avenue for the body to generate thermal energy. And by doing so, it increases the Q in the equation we saw before. Another thing that the body does, in particular the cardiovascular system, is that the blood vessels throughout your body contract. And that process lowers the blood flow that is occurring throughout your body. Now, if you think about it, your cardiovascular system is essentially a heat exchanger. It is attempting to take warm blood from the core of your body out towards its extremities and back. And by contracting the blood vessels, what is essentially occurring is that you are lowering the hydraulic diameter of the duct, or the, hypothetical ideal duct that you could consider to be your cardiovascular system. By lowering the hydraulic diameter, the equations and correlations for internal flow tell us that eventually the net effect is that this reduces the H, this reduces the heat transfer coefficient that happens between the body and the environment. Okay? When the ambient temperature, however, is too large, that means that the delta T, the difference in temperatures between the body and the environment, are too small. And we call these conditions hyperthermic conditions. In such a condition, the blood vessels expand, right? So the opposite of what happened before. Blood vessels begin to expand, and blood flow is increased throughout the body. Once again, if you think of it from the perspective of internal flow calculations, essentially what's occurring is that you are either increasing the mass flow rate or you are increasing the hydraulic diameter, either of which results in an increased value of the heat transfer coefficient between the body and the environment. To bolster this, your heart rate increases, which of course increases your mass flow rate, or at least the mass flow rate of blood through your body, increasing H. There's one other thing that the human body does in order to try to mitigate hyperthermic conditions, something which is super important, but that I will not talk about, at least not in this slide, simply because of the fact that what it does is so unique and important that it deserves kind of its own discussion. But in addition to this kind of unconscious process that the human body does, we also consciously perform external thermal regulation by manipulating the heat transfer coefficient ourselves. So what's a mechanism via which we do this? Well, consider fans, right? We use fans to cool ourselves off when we are in hot temperatures, and the fan is not altering the temperature of the surrounding air, nor is it altering the temperature of our body. What the fan does is it creates an ambient flow in the same way that we could consider an ambient flow over a flat plate when discussing convection and external flows. And by increasing the speed of this ambient air flowing over our skin, we are effectively increasing the heat transfer coefficient. This also happens whenever we take a cold bath. And the reason that I say cold is because if you think about it, what we really call cold water, like water that comes out of a tap in your bathtub, that water is not actually colder than the temperature of your room. That water has been exposed to the piping inside of your room for hours, if not days. So of course it's likely going to be in thermal equilibrium. It's going to have the same temperature. So that cold water is actually room temperature water. But the reason that it feels cold is because the thermal conductivity of water is significantly larger than the thermal conductivity of air. And what that essentially means is that when you replace the layer of air that's surrounding your skin with a layer of water, you are of course increasing the heat transfer coefficient between your body and the surrounding environment, which makes you feel cold, even though you haven't changed the temperature at all. Conversely, right, whenever things are cold, we wear jackets, we cover up. That provides an extra layer of material, and effectively, like if we replaced the layer of air surrounding our skin with a thermal insulator that has a smaller thermal conductivity and by extension decreases the heat transfer coefficient between our bodies and the environment. So these are the things that happen that we do consciously in order to try to either cool down or warm up whenever exposed to non-optimal ambient temperatures. But one scenario that a lot of people don't think about because it's a bit exotic is what happens when the ambient temperature becomes larger than our body temperature. Think about it, right? Heat flow occurs whenever there's temperature imbalances, and heat flow always happens from high temperature to low temperature. So what happens if a heat wave hits and the temperature of the environment is, 100 degrees Fahrenheit or 39 degrees Celsius or whatever, something larger than our body temperature? In that situation, heat flow now becomes reversed. The things that would normally cool us down by increasing H actually warm us up, because rather than accelerating the flow of heat out of our bodies, we are now accelerating the flow of heat into our bodies, causing a thermal energy accumulation that eventually leads to an increase in our core body temperature, which then, of course, leads to medical symptoms. Now, even though this is a very concerning scenario, nevertheless, the human body can survive in temperatures larger than 98.6 degrees Fahrenheit. People live in deserts, albeit, difficultly, and we can go into a sauna, which is at a temperature considerably larger than 98.6 degrees Fahrenheit, even if just for a short time, and survive. And the mechanism via which we can do this, the mechanism that the human body has for dealing with this scenario, is the mechanism that I had not really described in the previous slide, but which we will now do a little bit of a dive into, which is sweating. Sweating is the mechanism of thermoregulation that the body uses whenever it no longer has the ability to thermally regulate via the methods that I described before. And sweating, roughly speaking, can be described as just a process via which the body is expelling salty water, right? So water with a couple of, extra things in it. And that water that the body is expelling gets carried off by air due to the process of evaporation. And you can think of that water there, you can think of the process via which this happens in many different ways with different degrees of complexity. You can think of the idea that, the water molecules that are in your sweat have different, kinetic energies, and the water molecules that have the largest amount of kinetic energy kind of like shoot off from the drops of sweat in your sweat and go off into the air. And then they take their energy with them, which lowers the temperature and then effectively cools you down. You can also think of it as just a flow of matter that contains thermal energy, right? We had talked about the fact that, all matter has some thermal energy. And you can imagine that if you take, some sweat which has some thermal energy and remove it from your body, remove it from your system, that you are effectively leaching off thermal energy from your body or from the environment. Regardless of however complex you want to think about it, the net effect is the same. That the process of evaporation of sweat off of your body causes thermal energy to be leached off of your body, which effectively adds what is, if you think of the human body as a thermal circuit, it kind of adds a short. It adds another avenue via which thermal energy can be dumped other than directly into the environment. And the reason that sweating is so effective is because it works in a way it works both ways. Not only can it leach energy that the human body is emitting towards the environment, it can absorb or take more. It adds like an extra Q out in the energy balance that you would do. But it also takes energy that would be flowing into the human body from an environment that's warmer than the human body itself. And so regardless of which direction heat transfer is happening in between the body and the environment, the process of the evaporation of sweat is able to take some of that heat, is able to take some of that thermal energy and basically get rid of it, which allows the human body to be able to mitigate the effects of hyperthermic conditions, right? But it does depend on a key factor, right? Sweating is not the be-all, end-all of the ways that the human body regulates its temperature. It can't solve every problem because it depends on one key factor. It depends on whether or not the environment actually has the ability to siphon off that water, right, via evaporation. And the key thing that affects that process is humidity, or more precisely, the relative humidity. The relative humidity is just a measure of how saturated the ambient air is with water. When the air is at a 100% relative humidity, the air is fully saturated, which means that it can't hold any more water. Okay? The process of evaporation effectively stops because there is no kind of waterless air left to carry off those water molecules. And so because this happens, because evaporation stops, the mechanism that sweating relies on for, mitigating hyperthermic conditions stops as well. And so the process of sweating begins to work far less in environments where the relative humidity is very close to 100%. And just to give you an example of how close we can get to 100%, the relative humidity in places like New Delhi or Jakarta or New Orleans or even San Juan today was bordering on about 90%. And it can easily get to far higher relative humidities during heat waves, okay? Even reaching all the way up to 100%. And so when the relative humidity is close to 100%, sweating is far less effective because the amount of sweat that evaporates is much smaller than in dry conditions. And at 100%, it just completely stops, okay? And this makes it particularly challenging for people to regulate their temperature in the tropics or in humid conditions. It is the reason that humid air, at least in hot temperatures, feels so sticky and weird and unpleasant. It's because that hot, humid air interferes with your body's ability to thermally regulate by sweating. So now, let's start dealing with the actual ramifications of these things. Put yourself in the position of a person who is in the tropics, somebody who is living in a city where it frequently becomes hot and humid. What do you do in a heat wave where both the ambient temperature and the relative humidity of the environment are high? And for the purposes of this thought experiment, let's assume that the relative humidity is 100%, right? Let's assume that sweating fully doesn't work, okay? The instinctive thing that a person would do when facing, hot ambient temperatures is just to either fan yourself or to take a cold bath, to thermoregulate yourself externally, right? Because your body is undergoing heat stress, your body's trying as much as it can to try to, regulate its temperature via vasodilation, but it's not going to go all the way. So what you do instinctively is to fan yourself or take a cold bath. And the reason that these methods work is because they increase H, often by a very large amount. But the problem is that for high enough temperatures, once again assuming 100% relative humidity, for high enough temperatures, this actually makes things worse in a way that is kind of difficult to understand if you don't have at least a rudimentary understanding of heat transfer and how to model heat transfer. Think back to the way that we modeled objects and how temperatures change inside of objects as lumped thermal capacitances, okay? And think of the body as being a lumped thermal capacitance that has some thermal energy generation or heat generation that's happening inside of it. When you increase H, when you increase that heat transfer coefficient by fanning yourself, you are lowering, right, the eventual steady state temperature of the body. You are lowering the temperature that your body would reach at steady state under the conditions that you're considering, right? And ideally, you would increase that H, you would lower that steady state temperature down to a point where internal thermal regulation starts to work, okay? But the challenge is that it also lowers the thermal time constant tau. And the thermal time constant was this thing that was a measure of how quickly or how slowly the process of reaching thermal equilibrium happens, the process of heating and cooling over time. So, you're faced with hot temperatures and high humidity, and so you fan yourself and you take a cold bath, and for low enough ambient temperatures, this will be enough. This will work. right? It'll bring the steady state temperature down up to a point where internal thermal regulation can take care of the rest and keep you at 37 degrees Celsius. But what if the conditions are such that it's actually not enough? What happens if if you are fanning yourself or cooling yourself down in a bath and that's not enough? Well, of course, your body is going to undergo heat stress, right? You're not going to solve the problem. But in fact, what's happening is that you're making it worse, because now what you've done is that you've increased the H, which means that you've lowered the time constant, which means that you have increased the rate, the speed at which your body is heating up. So if you try to fan yourself, or if you try to cool yourself down in a bath, but you're not able to get that H all the way up to the value it needs to be, you are still nevertheless lowering the time constant associated with the heating process and causing your body to heat up far faster than it would in other conditions, making the situation worse. And so I like to call this paradoxical heating. One, because it feels like it shouldn't occur. It feels like when you increase H in a situation like this, it should be the case, of course, that it lowers your body temperature. But really what happens is that even though that can occur in certain scenarios, there are scenarios in which that increase is not going to be enough. And whenever that occurs, you're just causing the process of heating up, of the process in which your body fails to thermally regulate itself because its temperature starts to increase. You're causing that process to occur faster. Okay? So this is a very big danger because it operates against our natural instinct. Okay? But this isn't the end of it, right? This is a scenario where we are considering what happens if the ambient temperature is still below the body operating temperature, but is large enough that it causes paradoxical heating. What if the ambient temperature gets past 37 degrees Celsius? Now, as we mentioned before, the heat flow is reversed. Heat is now flowing into the body from the environment rather than from the environment. It's flowing now from the environment into the body rather than from the body into the environment. And that process is something that I like to call thermoregulative inversion. And the reason for this is because every process that your body knows, both your brain and, or I guess you could say the conscious parts of your brain and the unconscious parts of your brain, all of the processes that your body does now operate against you. Because all of the processes that we know how to do, both consciously and unconsciously, involve increasing H. But with the direction of heat flow reversed, increasing the H just means that you are warming up your body more and more. The only mechanism via which we can avoid this kind of thermoregulative inversion is by sweating. But we don't have sweating available anymore because the relative humidity is 100%. And so the voluntary behaviors of, fanning ourselves and taking a cold bath, and the involuntary behaviors of vasodilation and increased heart rate work against us. Fans become air fryers. Baths at ambient temperature, right, the cold baths that we could take in our homes, suddenly become deep fryers. Okay? And this process of acceleration is not something that is instinctual to us. Again, it is a fundamental reversal of everything that we instinctually know about cooling ourselves down or heating ourselves up, which makes it extremely worrying. So if you are a person that is in such an environment, none of the things that you would instinctively try to do would work. In fact, some of them would make the problem even worse. Okay? So what can you do? What are the things that you can do if you're exposed to a heat wave in these sorts of environments? Well, one of the only things that you can do is to lower the ambient temperature, right? And the way that you do this is that you try to go somewhere that's colder, if you can find somewhere that's colder, or you make where you are colder via air conditioning. And air conditioning is one of the very few ways that a person can survive these conditions without dying from heat stroke. Okay? There is no other tool that we have available, or at least not that many other tools that we have available to prevent this kind of situation from becoming a problem. other than, well, some things that I'll talk about later, but simply using air conditioning. So you use air conditioning. You tell your neighbor, hey, turn on your AC. They tell their neighbor, hey, turn on the AC. This is the only way that we're going to get out of this. And everyone in, your neighborhood and the neighboring apartment building suddenly realizes, hey, the only way that I'm going to survive is by turning on the AC. But the problem is that air conditioning units often use about as much power as every other appliance in a house combined. Now, this will depend, of course, on the nature of the house and the thermal insulation and all of these sorts of things. But the point is that AC units demand an enormous amount of power from the electrical grid relative to everything else. And electrical grids are designed in such a way that we assume that everyone won't be using their AC units all of the time. We operate off of the assumption that some people will have their AC units on during, heat waves, and some people won't. And we design it in such a way that, our power grids don't really accommodate everyone in a dense city using their AC units at the same time. And as a result, in a scenario where this sort of event happens, in a scenario where everybody thinks, I have to turn on the air conditioning, the most likely result is that the power grid fails, that the load that is imposed on the electrical grid is so large by the collective AC units that the grid fails. So no more power, no more air conditioning. And you might believe that these systems are not necessarily unstable where you live, right? And that might be true. But remember that we are talking about the grid in a lot of places where weather affects the stability of the grid. And I personally am Puerto Rican, so I'm very convinced about the fact that electrical grids can be very, very unstable. So now everybody's been using their air conditioner, they've been using it as a lifesaver, and now the air conditioner's gone. What can you do? What are the remaining techniques or things that you can do in order to try to save your life in this kind of extreme heat event? And the answer is that there's not that many. In particular, the fact that everybody has turned on their air conditioner means that you have effectively turned on a heat pump that is pumping heat from inside people's houses out into the environment, right? That thermal energy has to go somewhere. And where it goes is in ambient, making the temperature of the environment even hotter. So what are the few things that you can do when you are exposed to a scenario where these sorts of things are happening, but you don't have any power? Well, one of the things that I like to recommend the most is to consider the air conditioning units inside of cars. Right? Cars operate independent of the electrical grid, and they're mobile. So you can simultaneously cool down and then try to find a place where other people are congregating to cool down and deal with the heat wave as they go through it. This, of course, relies on whether or not you have gas in the tank. If your fuel tank is close to empty, then this really won't work. But the air conditioning units inside of cars are one of the few places where you can have a reliable AC unit that operates independent of the electrical grid. And the other more underrated thing that will help you in such a situation is a dehumidifier, as long as you can power it, right? And the reason that dehumidifiers are useful is because they lower the relative humidity of the air around you. So you drop that humidity from, say, 100% to, whatever number your dehumidifier is able to handle. And even if that reduction is small, it does mean that sweating starts to work again. And sweating, being such a powerful mechanism of thermal regulation, is something that, even though it won't necessarily make you feel more comfortable, it will help your body get through the extreme heat event. Okay? So what happens when the body starts to fail to thermally regulate itself? Well, the symptoms that begin are heat exhaustion. The collection of symptoms that occur when this thermal regulation begins to fail is referred to as heat exhaustion. In the process of heat exhaustion, your body temperature starts to rise. It starts to rise slowly from 98.6 degrees Fahrenheit all the way up to approximately about 104, at which we stop calling the process heat exhaustion and we call it something else. your body is able to handle, right, rises in temperature. I mean, we get fevers whenever we get sick, so it's not like we can't exist for a couple of hours at temperatures that are larger. But fevers don't feel particularly good, especially when it's not a voluntary reaction from the human body. And so as a result, we start to feel things like dizziness, fatigue, dehydration. Blood pressure starts to lower. We start getting muscle cramps. We start getting headaches. We start getting nausea. All things that happen potentially when we are suffering from fevers, right? The difference is that, as I mentioned before, a lot of the instinctive behaviors that we have for dealing with these kind of extreme heat events are counterproductive. And so as a result, when you are dealing with fatigue and dizziness, you might just revert into performing these kind of instinctive behaviors and then make the situation even worse for yourself. So you have to be extraordinarily conscious and careful about what you're doing, even in a scenario where you don't have as much of your cognition as you would like. After the core body temperature starts to rise past 104 degrees Fahrenheit, we then start calling the process heat stroke. And there, the symptoms, of course, become far more serious. You start to suffer full-blown delirium. You can potentially get seizures or blurry vision. It becomes very difficult to walk around. Your blood pressure lowers even more. You start to observe organ swelling throughout your body, including your brain. You see cellular damage occur throughout the body. And weak points are particularly the liver and the kidneys. So people who have weak livers and weak kidneys have to be extra careful about heat waves. And eventually, after continuous exposure to this sort of thing, you die. And so you can imagine the effects of an extreme heat event like the one that I'm just describing in a large, densely populated tropical city. Every single person inside of the city, assuming that the things that I've just said are true, will be affected by the symptoms that I'm describing here, assuming that the conditions become as worse as I just described. And without the presence of a reliable electrical power grid, there really is no consistent mechanism of recourse to try to help prevent these sorts of things from happening. And so there is the real possibility of mass casualty events that could occur as a result of these kinds of extreme heat events that I'm just describing. Now, when do these kind of events occur? What is the threshold via which they occur? Well, remember that the human body is different, right, between every different person. And so the conditions in which paradoxical heating and thermoregulative inversion occur for a given person will be different. The World Health Organization provides an approximation of the threshold for when these conditions occur as a wet bulb temperature of 35 degrees Celsius. Now, the term wet bulb temperature is kind of weird. All that wet bulb temperature means is that the wet bulb temperature is the temperature that you read off of a wet thermometer. So you take a thermometer, you dip it in water, and then you try to measure the temperature. And the reason that this affects the measurement is because of evaporative cooling, right? So when evaporative cooling is taking place, the temperature that the thermometer is going to read is going to be smaller than the actual temperature that you would measure from a dry or normal thermometer. But at 100% relative humidity, the wet bulb temperature is the actual temperature. And so when the World Health Organization says that the threshold is about 35 degrees Celsius, or a wet bulb temperature of 35 degrees Celsius, what that really means is that the threshold is 100% relative humidity and 35 degrees Celsius, or temperatures that are slightly higher and relative humidities that are slightly lower. So it's actually kind of a spectrum of thermal conditions, okay, that is described by this wet bulb temperature threshold. And it's kind of interesting to think that thermodynamicists in the past used to think that these kinds of conditions didn't occur or couldn't occur sporadically on habitable parts of the Earth. That these sorts of things, that London or, Europe or wherever couldn't be affected by sporadic heat waves that caused the wet bulb temperature of the environment to go past 35 degrees Celsius, largely because they believed that the human body and that bodies, wouldn't be designed or wouldn't have evolved, in the way that they did if such conditions could take place. And it's very curious to think about the fact that around the time that when they were making these predictions, this prediction that this couldn't occur, the Industrial Revolution was also happening too, which we know now is the key driving factor in man-made climate change. Whatever or however large you think that impact is, it is nevertheless, of course, the key driving factor associated with man-made climate change. And so these thermodynamicists used to think that these conditions couldn't occur. And using data that has been taken from airport thermometers, which usually tend to be very good and very comprehensive, we can list a set of places around the world where these events have actually occurred, where we have measured a web bulb temperature that's larger than 35 degrees Celsius for at least an hour or two, okay? And you can see that the events occur in this, for the most part at least, in this band slightly north of the tropics, which is expected. The tropics is the environment in which, we expect to see hot temperatures and, humid atmospheres. And so these things, these phenomena are already potentially occurring. They are not occurring in places which are, densely populated enough, or they are not occurring for long enough times for us to realize that these things are actually extreme heat events. They seem like they're just normal, really bad heat waves. But the conditions for which these catastrophic events can occur is already happening throughout the planet. And if you believe that climate change is just going to get worse, that the average temperature of the Earth around the tropics is going to get larger, these events are only going to become more extreme. They're going to last longer, and they're going to occur in more and more places, including dense cities in the tropics. So if these events occur, if it does unfortunately become the case that mass casualties occur as a result of extreme heat events, it is quite likely that politicians and people in power will parade to the press and say, how could we have known? I didn't know that something like this could happen. How could we have known? I didn't know that this could occur. Maybe they're lying. Maybe they're telling the truth. Maybe they didn't actually know. But you know. And with that knowledge comes the responsibility to do good, to try to solve this problem, not just because you have a responsibility to the people who live in these locations, but because you have a responsibility to yourself, to your conscience, the part of you that believes that you are a good person. Ignorance is by and large the chief excuse of inaction. It is the thing that people rely on the most whenever a tragedy, a preventable tragedy occurs, to try to excuse the fact that they didn't do anything about it, to alleviate themselves of that responsibility. But you, just like I, are now carriers of this responsibility. And as a result, we now have to go out into the world and try to do what we can to solve this problem, whether it be by dedicating our lives or our careers to finding concrete solutions, developing kind of societal changes that allow us to prevent these events from occurring, or whether or not it just involves doing what I'm doing right now and communicating the possibility, the mechanism via which such events could take place to more and more people. You can't dodge that responsibility the same way that I can't either. So take the knowledge that I've given you today and try to do good with it.